Hi, my name is Crystal Anderson. I'm an attorney at Frankly Legal and a student at Harvard Extension School. I'm here to present my final project in the Deep Learning course in fall 2025 on the topic of AI legislation and governance, or more specifically, counterfactual fairness testing for developers as a form of internal governance. So, this project sits at the intersection of artificial intelligence, law, and public policy. And rather than asking whether AI systems are fair in an abstract sense, this project is asking a more legally relevant question. How can AI developers demonstrate that they exercised reasonable care, a term we see over and over in the legal field, in identifying and assessing discrimination risk during model development? And that's just, one small aspect of governance, but it's something that I could focus on here. So to answer that question, I am going to present a short legal and governance analysis of the United States AI regulatory landscape and a concrete deep learning method, counterfactual fairness sensitivity testing, as a partial solution for developers. So, to understand why this is needed, let's start with how AI is governed in the United States. So, unlike the EU, in the US, there's no single comprehensive AI statute. Instead, AI governance emerges through a fragmented framework. It comes through civil rights law, here, employment discrimination statutes, consumer protection law, state level AI laws, such as those in Colorado and Texas, procurement requirements, and largely litigation, where courts are increasingly examining AI systems after alleged harms occur and creating, more regulation after the fact. So that means AI governance in the US is largely ex post and evidence driven. Here, developers are rarely asked to prove that their systems are perfect. Instead, they're asked, did you anticipate foreseeable risks? Did you test for those risks? Can you document what you did? This is especially important in high impact decision contexts like employment screening, income classification, creditworthiness, and housing, areas where discrimination law applies, and those are heavy federal laws. A key shift that we see is that it is developers, not just the deployers, that are coming under scrutiny. Courts and regulators are increasingly asking questions about training data, feature selection, pre-processing, and evaluation practices. So, there's more efforts to put the burden on the developer, but there's a governance gap. Developers have to show reasonable care, but there's no clear technical standard as to what that looks like. So the problem here is from the machine learning side, there's a lot of fairness and fairness metrics and techniques, but a lot of them are difficult to interpret legally or are focused on deployment outcomes rather than development practices, or they require complex causal assumptions that are hard to defend in court or regulation. Developers need a developer side deep learning evaluation method that mirrors legal intuition, is legally simple, and produces auditable evidence so that the, you know, courts can come in and say, look, yes, the outcome would have been different if the person belonged to a different protected class, or no. Um, because there is on the legal side a lot of intuitive reasoning, often framed in but for terms like that. So the answer that I propose here is counterfactual fairness sensitivity testing. It matches kind of the legal framework of would the outcome change, but for that person being different. And that's useful in the employment context, housing, anywhere where there is a discrimination issue or fairness issue. Um, so this is a narrow like proposal. It doesn't, cure all reasonable testing efforts for a developer, but it's a usable method that can provide evidence for a developer. So at a high level, this is how the model that I put together works. We trained a simple deep learning neural network, identified a protected attribute. In this project, we used sex. And for each input example, we created a counterfactual version where the protected attribute is flipped while all other features remain the same. And then we run the model on both versions and measure how often and how strongly the model's prediction changes with just that quick turn. The key idea here is isolation. We're changing only the protected attribute and observing whether the model's behavior changes. This does not claim causality or prove discrimination, but it measures sensitivity, whether the model's output depends on protected status in ways that may create legal risk. And this aligns closely with US legal reasoning and governance expectations. To demonstrate this method, I implemented a deep learning pipeline in Google Colab. For my data set, I used the UCI Adult Census Income data set, which you're able to access using the Fetch OpenML code. The data set predicts whether an individual earns more than 50,000 per year based on demographic and employment features. While it's not a production employment data set, it's pretty widely used in fairness research and serves as a good proxy for high impact socioeconomic decision making. Exactly the kind of context that triggers heightened legal scrutiny. So for the model, I used a simple feed-forward neural network. This choice was intentional, even though relatively simple deep learning models can encode bias, and governance does not require a complex architecture to raise legal questions. And using a simple model makes the evaluation transparent, reproducible, and a good example for developers. So this model is trained using, standard practices. We did some pre-processing, train test split, performance evaluation, and some reproducibility controls. I didn't include that on this slide. This is just the basic model code, but it is used for, the goal of some behavioral analysis. And we're not trying to optimize and show how this works on a super complex model here. So again, these are important. I think reproducibility is going to be very important in the governance context because if you get pulled into litigation, you may be asked to, repeat, show what you did. How was it not, how did you test for bias and can you do it again easily? We do the train test split so that we can audit integrity. We document the pre-processing and keep record of all performance metrics. So after training the model, we conducted a counterfactual fairness test. Here's what happened, basically step by step. You take the data set and create a counterfactual copy just flipping sex, male to female, female to male. You keep everything else constant and unchanged. And then you run the trained model on both data sets. Then you complete 3 metrics, right? The counterfactual flip rate, which is how often the predicted label changes, the average probability change, i.e., how sensitive predictions are even if the labels don't flip, and then a directional effect, whether flipping tends to advantage or disadvantage a group. These metrics are not judgments of legality, they are just diagnostic signals. But from a governance perspective, the key outcome is not the numeric value itself, but that the developer can say, we tested whether our model's outputs are sensitive to protected attributes And here's the documented evidence that, that protected attribute isn't making a huge change. So here's the visualization that I put together using my model, just the probability after flipping just sex. And then there was, minimal sensitivity. So um, it worked out fairly well here. So this is where the technical work can connect directly to law and policy. In the US, you really would want to have evidence of everything that you're doing from the governance standpoint. So state laws want you to identify risk and document your efforts to use reasonable care in that respect. You may want to maintain evaluation artifacts, which is the report that I created here as an example. And when you're, in a litigation case and there's discovery and depositions and things like that, you want to be able to have that proof to defend yourself. So counterfactual fairness testing produces these kinds of governance artifacts, evidence, reproducible metrics, documented procedures, interpretable outputs that can be, you know, presented to customers so that if they get sued, they can help defend themselves, and you can use it in your own litigation defense. It's a potential, sales benefit when you're trying to sell your model or license it out to others to use. You could say, look at all this um, evaluation and testing that we did to make sure that we're compliant with all these discrimination laws. So this approach is helpful because instead of freezing innovation out of fear, waiting for strict guidelines to come out from the court systems, you're using process documentation and reasonable care so that no one can say you were negligent while waiting for these kinds of laws to become more structured. So this will, like I said, um, it aligns with what the state AI laws require, like risk assessment and mitigation planning, and that allows for more innovation in a time when the AI legal field is uncertain. So, some pros and cons of counterfactual fairness testing. It is legally intuitive. It's developer side, so it can be conducted pre-deployment. It's reproducible. It's low cost. You could see how simple it was in the steps slide that I put together. And it supports high-risk AI risk assessment and reasonable care expectations. But cons, it is not proof, right? We're showing sensitivity. It doesn't show, whether there was real world discrimination somewhere or legal liability in that respect. Ah, it is sensitive to feature correlation. So flipping attributes could, in some cases, create unrealistic combinations, um, depending on what all of the data is. The proxy variables, if you remove one attribute, it may not eliminate indirect bias. The results can vary based on decision cutoffs and all of the data going into the model. And it's really incomplete on its own. It's one step, as I was saying. It should be combined with group level metrics, mitigation strategies, and any other deep learning model that might be able to help add to this pile of evidence that you used reasonable care. So again, it's not causal proof, does not completely eliminate bias, and proxies remain. But with several layers of group fairness metrics, it can be a a large part of an overall reasonable care scheme. So for future work, maybe developing and this is really dependent on the field that you're working in, but a model of multiple levels of testing that, for example, employers can use to ensure that, um, or developers of programs for employers can use to show that their system is as fair as possible. Also, in terms of legislation, there could be bills proposed, for example, to require such forms of testing, because this risk is certainly foreseeable. All right. In conclusion, this project demonstrates that deep learning evaluation can function as governance. In the United States, AI developers are governed less by prescriptive statutes and more by what they can prove after the fact, about what they foresaw and tested for. So, counterfactual fairness testing provides a method that's technically feasible, legally intuitive, and evidentiarily robust. And so by integrating this kind of testing with as many other technically defensible forms of testing that they can for any reasonable risk from whatever they're developing, they can, better align what they're doing with the evolving legal and governance expectations. And not by claiming perfection, but by demonstrating responsibility so that there's less question in the future of the issues that may be caused by AI development. Thank you so much for listening to my presentation. Have a great day.